Hi friends, welcome back to my channel Connect with Civil.
Design of square isolated footing.
Before proceeding to the design steps, let's recall few things from the part 1. This is the question, basic data given in the question, size of the footing we have calculated and thickness of the footing.
Let us start the flexural design now. The critical section for flexure is located at the face of the column. The caudal reference is given in the bracket. Refer the figure in which the red line indicates the critical section. The bending moment at the critical section can be obtained by calculating the moment of forces acting over the entire area of the footing on one side of the vertical plane passing through the critical section. Let's calculate the bending moment now. We know net factored soil pressure is equal to 0.383 Newton per mm square. Coming to the area, in the figure, shaded area refers to the area on one side of the critical section. So we have to consider the force acting over this area. The factored moment at column face can be calculated by multiplying the force acting over the shaded area into the distance of the force from the critical section. Multiplying the net factored soil pressure of 0.383 Newton per mm square with the area of the shaded portion, that is 3000 into 1275. We can get the force acting over the shaded area, and this one multiplied by the distance from the critical section, that is 1275 divided by 2, will get the factored moment at column face, that is equal to 933.92 into 10 raised to 6 Newton mm. We have calculated the bending moment at critical section. Next, let us calculate the moment coefficient R, which is equal to mu by BD square, where mu is the factored moment that we have calculated just now, and B is the width of the footing, that is 3000 mm, and D is the effective depth of the footing, that is 659 mm. We will get the value of R as 0.717 Newton per mm square. Now we can calculate the reinforcement required in terms of PT. We have a formula for PT, that is PT required divided by 100 equal to FCK by 2FI into 1 minus 4.598 R by FCK, where FCK is equal to 20 and Fy is equal to 415 and R is equal to 0.91717. On calculation, we will get the value of PT required by 100 is equal to 0.208 into 10 raised to minus 2. So, PT required will be equal to 0.208. We know the minimum area of reinforcement is equal to 0.12% of gross area of footing. So, 0.0012 multiplied by 3000 into 750 will give the minimum AST required, that is 2700 mm square, which is, so from this we can calculate PT minimum, that is we know 100 PT is equal to 100 AST by BD. So on calculation, we will get the value of minimum PT as 0.137, which is less than our requirement, that is 0.208. So PT from flexural consideration is 0.208 and one-way shear consideration is 0.25, which we have assumed while doing the one-way shear calculation. So we can consider the greater one here. So PT is equal to 0.25 since there is no much difference. If we have so much of difference, we have to redesign the section. So we know PT is equal to 100 AST by BD. From this we can calculate AST is equal to PT into BD by 100. So we get the value of AST required as 4943 mm square. Next is the calculation of development length. In order to develop the full design stress in the bar at a section, a minimum development length LD is required on either side of the section. When the required bar embedment cannot be conveniently provided due to practical difficulties, bends, hooks and mechanical anchorages can be used to supplement with an equivalent embedment length. That is what we are checking here. We have a formula for development length according to clause 26.2.1 of IS 456-2000. According to this, LD is equal to 5 sigma s divided by 4 tau BD, where 5 is the nominal diameter and equal to 16 mm in this case. Sigma s is the design stress and it is 0.87 Fy, where Fy is 415 Newton per mm square. Tau BD is the design bond stress and clause 26.2.1.1 gives the value for this. According to this clause, for M20 concrete and plain bars, it is 1.2 and for deformed bars, we have to increase this value by 60%. That is 1.2 into 1.6 will be our tau BD. Now, we can calculate LD considering all these values and it is equal to 752 mm. Now, we have the required development in hand and we have to check whether the length available will be sufficient or not. Length available from the critical section, that is from the face of the column to footing end, is equal to 1275 minus 75, where 75 is the clear cover, which is equal to 1200 mm and it is coming greater than the development required. So enough length is available on either side of critical section. So there is no need to provide additional provisions like bends, hooks, etc. Next is the transfer of force at column base. Here, we have to compare the factored axial load Pu with the limiting bearing resistance FBR of concrete to check whether the full force transfer can happen without the need of any reinforcement at the interface. Pu is equal to 3450 kN. Limiting bearing resistance can be calculated by multiplying the limiting bearing stress with the area. We have a formula to calculate FBR max. Here, A1 is the supporting area, A2 is the loaded area, and the value of root A1 by A2 should be less than 2. If we are getting more than 2, we have to consider the value as 2. In this case, at the column footing interface, we have to consider column face as well as footing face. The value of A1, A2, root A1 by A2 and FBR max are tabulated both for column face and footing face below. In the table, we can see FBR max is less in the case of column face, that is 11.25 Newton per mm square. Since it is resistance, we have to consider the lesser value. Lesser the resistance, more is the failure chance. So, we can calculate limiting bearing resistance FBR as 11.25 into 450 by 450, that is column area. We will get the value of 2278 kilonewton, which is less than our factored axial load. Since the resistance is less than the load, the reinforcement should be provided for the transfer of full load at the interface to happen. We can do it in different ways, like extending the column bars into the footings by using dowels, etc. In this case, it is convenient to extend the column bars. Just we have to check if embedment length is available or not. So we have 8 numbers of 25 mm dia bars as column reinforcement. The excess force to be transferred by the column bars is equal to load minus resistance, that is factored axial load of 3450 minus limiting bearing resistance of 2278, which will give you a value of 1171.88 kilonewton. Now, we know the equation for development length is LD is equal to 5 sigma S divided by 4 tau BD. In this case, phi is equal to 25 mm, that is diameter of the column bars. Sigma S is the stress in bar at the section considered at design load, and we are considering partially stressed bars here. So it will be 0.87 Fi into delta Pu by Pu, where delta Pu is the excess force to be transferred, that is 1171, and Pu is the factored axial load. Tau BD is the design bond stress, and for M20 concrete and plain bars it is 1.2 from clause number 26.2.1.1, and for deformed bars we have to increase it by 60%, and for bars in compression it has to be increased by 25%. So here the value of tau BD will be 1.2 into 1.6 into 1.25. On assigning all these values in the equation, we will get the value of development length as 319 mm. We have calculated the required development length as 319 mm. Now let's see the embedment length available, that is equal to effective depth of 659 mm, which is greater than the development length calculated. So we can just extend the column bars into the footing and provide a 90-degree standard bend, and it can rest on the top of the footing reinforcement layer. The figure shows the extension of column bars. The bars are extended from the column footing interface till footing reinforcement and given a 90-degree standard bend so that it will be resting on the footing mat. We have calculated the reinforcement area required. Now let's distribute the reinforcement. AST required is equal to 4943 mm square. If we are using 16 mm diameter bars, number of bars can be derived by dividing the AST with the cross-sectional area of 1 bar, that is pi by 4 into 16 square. Doing so, we will get 25 numbers. Next, we have to find the spacing and check whether it's coming in between the minimum and maximum limit. By subtracting the clear cover and half the bar diameter on both sides from the length of the footing, we will get the length where the reinforcing bars has to be distributed. And this length divided by the number of spacing, that is 1 less than the number of bars, will give you the center to center spacing. So we got 118 millimeter, and it is greater than the minimum limit of bar diameter and less than the maximum limit of 300 mm. So we can provide 25 numbers of 16 mm dia bars both ways. The figure shows the distribution of footing reinforcement, generally called as footing mat, in the plan as well as in the section. Here, red lines indicate the reinforcement along one side and blue lines or dots along other side. So we have completed our design part. Here comes the detailing. Here the footing dimensions and distribution of reinforcement are shown in the plan. This is the sectional representation of the same. The red lines indicate the footing reinforcement along one direction, and the blue lines or the blue dots indicates the footing reinforcement along other direction. These black ones are the column bars which are extended into the footing and rest on the footing mat. Here is a picture of a similar kind of footing showing the distribution of reinforcement. So this is the shuttering provided along the periphery. These are the footing bars. These are the footing reinforcement, generally known as footing mat. And these are the column main bars which are extended into the footing, given a 90-degree bend and are resting on top of the footing mat. And these rings are called the stirrups. This is just for your information. Stirrups will not come under the purview of footing design. We have to consider all these while column designing.
Till here we have done in part 1. Now let's revise the steps explained in part 2.
Next is the flexural design. Here the critical section is located at the face of the column. So calculate the bending moment and corresponding reinforcement requirement. Finalize the AST to be considered after comparing the values from flexural consideration, shear design and minimum requirement. Then distribute the bars accordingly. Calculate the development length required and compare it with the available embedment length. If the development length is coming more than the embedment length available, we have to consider providing hooks, bends, etc. Now check the force transfer at the column footing interface. For this, compare the factored load and limiting bearing resistance, and if the load is greater than the resistance, we have to go for reinforcement. Final step is the detailing part. Thank you.